Hi everybody, Dmitris here. So at this point we have our calibration file for the rig definition with all light positions. We have a ground control point set up for reality capture. So at this point let's go ahead and try to build our first prop, which is going to be that color chart. Even though it was not photographed specifically to build the prop, but mostly to do this calibration related stuff, because it only has a single loop there, which and only 12 shots. That's clearly not enough to build a high quality mesh, but we can still build something quickly to validate the whole process and see how everything works before we go ahead and start building a more proper, that complex octopus prop. So in this case we have that ground control reality capture scene, but let's start a new one so I can show you how to use that ground control point file that we created. So we start reality capture. Let's go ahead, and this time instead of just a PG image we'll use image with DMAD extension. That's gonna give us a little bit better mesh quality in reality capture, even though typically with things like a Metashape, where you can use different image sets for different processes, we would use these 3 image sets for image alignment and other ones that have higher bit depth, but more optimized for building better meshes using photogrammetry process. It's possible to do that with reality capture as well, but it's a bit more tricky stuff that you need to do there, because even when using layers in reality capture, it doesn't allow you to use different image sets for alignment and for mesh reconstruction. Anyway, here we'll use this set of images. There you go, they're imported. Let's make sure that all the groups are aligned. Yeah, everything is assigned to group 0. Next thing that we want to do is under alignment detect markers and click detect, making sure that we have proper tag family selected. There you go, everything is detected. We got our 20 control points. Now under import we go import ground control, and we go to this main box GC file that we exported in the previous videos, and let's open that. Make sure it's the same format, comma separated, XY altitude, coordinate system, Euclidean. Everything looks good. So you can here also see the default accuracy for X, Y, and Z, which is set to 0.01, and that's going to be, I believe, 1 centimeter, but we could improve it to set it to like 1 millimeter, but or just leave it as default 1. That's also fine. Click OK. And now we can see like these georeferenced icons next to all our control points, and at this point we can go ahead and click align images. And there you have it. So right now not only it aligned everything, and it's all in a single component, which is great. Let's make sure that actual camera positions are good and they form a good circle there, and there are no outliers or weird cameras. In our process we have some ways to validate that, but it's still good to check and make sure that it's what is expected, and in this case it's pretty much all good to go. Let's build our preview model, but before that let's save it and call it the chart, just like that. Now go ahead and build preview. That's obviously not a good model, so go ahead and build in normal detail, and hopefully this model is going to be more useful so we can proceed with building the actual prop out of it. And we are almost done. Let's see what that mesh looks like. It looks almost okay. There are some outliers there that might need to clean. Another thing that we would want to try real quick, if under mesh model, create mesh settings, we can go ahead and there's depth map algorithm version, and let's try version 2. I don't remember which one is the default one. It might be 2 in later versions of reality capture, but the cool thing is that you see here is that the using those ground control point, that the mesh is nicely aligned and oriented, so we don't need to do anything extra there. Anyhow, let's try this algorithm number 2 for depth reconstruction, and let's pick the model that we like the most out of the two. And there are some extra settings here that you can play around with. As I said, in this case, it's better to use a different set of images that have some specularity in there as well. That usually helps with a depth map reconstruction, but it's not very useful for alignment process. And if you have any speck in there, especially on some kind of black plastic like this that's also shiny, the alignment process has no chance there. Well, this one might be a little bit better, hard to tell. This part in the back looks a bit strange. So maybe we just go ahead and use this model. I'm still kind of surprised why. No, all the cameras are well aligned. I guess it's the image set. We can also let's try quickly building another one as well using original images. Maybe that would give us a slightly better result. So instead of these, let's use these ones. Let's do the same stuff. Detect markers, detect. Great. For some reason we have 21, and that's because we have this outlier now that we had during calibration process, but we can ignore that. But before that, we need to import our ground control points, so that one is ignored because it's not in the set. Let's go ahead and click align. What have we got? Great, single component. That's good. Let's look at our cameras, and that is not good. So we obviously can see one camera that's very far off, even though everything is aligned. So that is the kind of stuff we have to pay attention to. So we have these poses, and that's obviously not good. We can go ahead and try to run it one more time, and this time everything is good. So, and you would see when you run these things, you would see that sometimes even without changing anything, you run it a second time, you would get a different result. And the reason is that a lot of these algorithms in photogrammetry and optimization in general, some of them use some random seeds, and in other cases, especially when it runs on GPU, you cannot guarantee that things are always there are cases where you keep running the algorithm and it will keep converging, or you rerun it and it will end up with slightly better or worse result. And that's common not just for reality capture. It's similar with Metashape, as we'll see, where we run the process the second, third time and we'll get better and better results, but sometimes we get worse and worse results, and then we have to go back and constrain it more. Anyway, in this case everything seems to be fine. Let's go ahead and also build our normal detail mesh, but this is right now using different sets of images. I'm just trying to basically see if we could get a better results, but as I said before, we would have to use really different image sets there, but in reality capture currently these two images that are essentially 16-bit TIFFs, they do have some view dependent components there, so alignment will not work out of the box, and we will cover those cases kind of in a special advanced sections of the processing, where you can start doing tricks of using one image for one set of processes and a different set of images for different processes, and that way it's possible even without using structural or laser scans. You can still get much better results out of photogrammetry. So this is, I guess, mesh using algorithm number 2. Yes indeed. Let's also try algorithm number 1. Let's see if that one would look a bit smoother there. As you can see, the interior is definitely smoother, but we have this outlier here. So I think just to look at the front of this face, we'll go with this model. That's probably it's definitely not scanned for that, and we're not using the proper image for mesh reconstruction, but I would say let's just clean this up a little bit and go with this one. So we're gonna close this project. We don't need this one anymore, so that was good. We go to our thing and let's remove some things that we don't need in this mesh. It's probably also, let's cut all that stuff from the top. As we would mostly be interested in the actual color chart part. Filter that. And we can probably also cut a bit from the bottom there as well. Maybe something like that. Great. I think this will be good for our initial set of tests. And let's remove all those other models. This one is going to be used for reprojection, and we treat it as a high poly model. Let's go ahead first and export our registration. In the chart, let's override our RC cameras file. Okay, let's save this project into what we had there previously. Done. So this is our high poly model. Let's call it here high poly, so that we know what it refers to. And now for the low poly one, technically we can take the same model and just generate UVs there, but usually when rendering all that photometric models, we get all that realism and all that detail from textures. So technically we don't need millions of polygons in our models to make them look realistic. So we can just simply go to simplify tool and say like 100,000 polygons is good enough for this model. Click simplify. So there you go. We call it low poly. This is just for the reference. It doesn't mean much here as well. So that's our high poly, our low poly, with just 100K triangles. And at this point, we now want to go to mesh, and we want to do unwrap to generate a UV texture set there. And we specify some glider, which is the distance between these UV charts. Max resolution is 8K, and important parameter at this point is maximal texture count is 1. Even though we support UDIMs and other sets of textures, but it's a bit easier to work with when you have a single texture to start with. So let's click on wrap and assign some checkerboard to that, so we can just make sure that everything looks good there. Yeah, some things we don't care about. As I said, we don't worry about the quality of this particular mesh at this point, because this is not the point of this tutorial. So we got our high poly, low poly. We just exported our registration information. Now let's click on our high poly mesh and export. It says here dense mesh model, but another way is under tools, export, mesh and point cloud. That should be the same. So, and we export our high poly mesh into this _high PLY file, and it should be binary. We also export normals here as well. Coordinate system grid plane. As for everything else, the rest is whatever we have there by default. So that's exported. Now let's click on low poly mesh, go to tools, export mesh, and the low poly one will be under .obj with UV maps and texture coordinates. Normals as well. That all looks good. Under texture settings, yes, export textures. We don't really care about the actual format there. Click OK. So everything should be good. Let's just save it. Now we exported registration. Let's run this RC camera CSV to camera batch file, and at this point also run marker info, since we updated the registration. So it went ahead and modified the file, and I figured all the parameters. So at this point we have our low poly mesh, high poly mesh, and our registration, and we're ready to go and start building our first set of data. We do have under solve 001, that's the default one, resinfo script, which will go ahead and try to calculate the optimal texture resolution for the data set and images that we have. Here we have this error, PLY element size 27 is not aligned. That has to do with how different exporters work. So in this case we have to go back and click run the script, fix up _high PLY, and that will go through that exported model and does some reconditioning so that the rest of the processing would work reliably. So let's run that resinfo again, and now it seems to work. Right now just building some acceleration structures that get cached, and in this case we see that, assuming that all our source images have perfect sharpness in them, then optimal resolution for that UV layout that was generated would be basically close to 7K. In video games, we like to work with powers of 2 textures, so here you can say like, well, it's either 4K, but it's a lot closer to an 8K texture. So we know that assuming that our source images are perfectly sharp, then 8K would be a good probably good output build for the final. But if images are not perfectly sharp, probably 4K would be the max that we can get out of that. So here we also have bounding boxes of our low poly mesh and high poly mesh that we can also quickly inspect and make sure that okay, that looks about the right sizes, so nothing weird happens here. So at this point, let's go ahead and quickly build a 1K texture. All the build settings are specified in this params file, and something in here. So there's basically symbols. Forgot what they called, prison cell doors. I forgot the name for these. These are comments, so everything after them is commented out. We have our scale specified here. We have exposure, and we have distance to that exposure plane that you don't have to specify, but in this case it's done automatically. And then this file basically has pretty much everything predefined already, depending on for those names that we set there, where you have low poly object with UVs, high poly one, camera registration information, rig definition file, the path to all our source images, and the rest are just some settings that we use by default that one can play with, and some of the more advanced ones that we would look at later to deal with various artifacts and edge cases that we can ignore for now. And we have a folder with masks. That's one we'll look into more advanced processing of masks, and some also dealing with edge cases where we have to use support structures and then remove them. And at the very end, that's the deployment stage where the final set is generated for different engines and different basically standards, where we have Sketchfab, Unreal Engine, Metallic versus Specular, Pipeline, and so on and so forth. That type of stuff we'll look at later. For now, usually it's best to start with like a 1K or 2K texture. At this point, we just click a build, and it will go ahead and read all our source images. And one parameter here to look at is this SPP at the end. That's sample per pixel, and if we only had a single shot and 12 lights, we would have the value of around 12, and essentially that value translates to how accurate all that PBR reconstruction is going to be. For most of the props, we have that value around 50, 100, in some cases even 200 when we want more precision there. It finished the core process, and then it went through all the kind of housekeeping stuff where it would dilate the textures. And if we go one folder up, we would see all our textures basically generated in here already, so we can recognize some parts of the color chart here. This MSR texture, even though some folks might assume that it's like metallic specular reflectance or metallic smoothness reflectance or specular roughness and so on, that's just a legacy name. It doesn't really mean much. It just multiple channels are exported, but we do have something that's properly extracted, which is a normal map, a photometric normal map. The tangent space normal map is generated from that. It's mostly used for preview. This is not the final set of data, but rather intermediate. Here we have reflectance texture, which is F0 reflectance, and we have a video that explains how all these values translate between different engines and how would you use it for calibrating shaders as well. We have GGX roughness here as well, and in this case our S texture is just the color component color of that F0 of zero specular, so it's not the texture that you would use right away or directly for anything like that. On the raw folder, that's what comes directly out of the photometric inference engine. This set of data just stays here and used for some processes under the hood, but this is what is generated directly by that engine. And one thing that's important here is this our W texture. That's essentially our confidence map, and when it uses green and red channels for primary estimates. So essentially when you see yellow here, it means it's very confident, and that's good data if you want to even cut it out into pieces and use it as in your material library. Green means that we did not have enough data, but it tried its best. So the model would still look correct, but you wouldn't want to cut pieces out of it and start using it for some other like texturing steps. When you have completely dark black areas, it means that I have no idea there, so it's still valid data in a way that it's going to be consistent, but it's going to be more biased and view dependent. The model would still look correct, but you should not rely on that data. There is a lot of kind of extrapolation and guessing there on the software sides of things. And then we have blue channel, where that essentially when it clips, we would have this white, like kind of white areas, and in those cases, some parts essentially we have parts of an image that clip, and there's not much we can do there. Let's say if you have a white piece of paper with some specular there, the signal to noise ratio there during this cross-polarized, the separation is so little. In some of those cases we have very little confidence in what we're looking at, and things might also clip. So when you see something blue like that, sometimes we just use it as a mask for some manual adjustments there. So this map can be very useful when working with the data. So and as I said here, this is intermediate stuff. Let's say if for some reason we go and kill our tangent space normal map, we can always go back and click build, and it will detect that that map is missing, and it will generate it from the primary photometric normal one. And we also have here just the one that's projected from the high poly, and it's not really used. It's mostly here for the reference, and when in very, very tough cases when you need to do some manual cleanup, it might be useful, but this data is not really used heavily, except for one process that I'll talk about later again. Also here, what we can do, completely kill those two maps, go ahead back to our build script, and now it will reconstruct that photometric one just from the raw data. So again, that didn't take too long. So anyway, that's just the overview of what these maps are in here. We have a special case that merges different sets of colors. So if you could see, we essentially have two albedos. In this case, it's hard to see the difference between them, but essentially one of them tries to focus on sharpness, and another one tries to look at the smoothness in some complex areas. So a typical kind of solution there is that we look at different frequency components there and combine them together, so that all the sharp stuff stays sharp, and all the kind of fuzzy stuff stays fuzzy. So we have a script there that you can run it won't hurt, but that essentially combines different things together. Then we can build a displacement that we'll look at later in more detail. We can go ahead and also bake this AO. This is not something that's it's mostly designed as a quick preview and something that we use on Sketchfab, so that in some cases it's usually it's easy to see the details on the model that way. So once that is done, we can click this script that will open Blender for preview, and in this case everything would already be pre-set up correctly, so and the model would be properly oriented. We can go ahead, move around, and we'll look at as you can see, this the plane of this model. When we look at this color chart, we definitely know that it's very flat, but when we look at this case, it looks kind of weird, and you would say like, well, that doesn't look right at all, like why it's all wobbly, and we'll look at that in a second why it is so. But if we switch to our solid, just a regular view, we would see that this is essentially our AO here. This is our object space normal, tangent space normal, albedo map, and in this case we would also want to take a screenshot and make sure that this particular color chart here has a value of 40 in lap space in Photoshop, again because it's albedo, it doesn't have specular component. Normally that value would be around 50. That's our roughness, that looks pretty consistent, reflectance, and that's our color. And if we zoom out a bit, this is going to be our confidence map, and here we could estimate and see where the problems are and what's reliable and what's not reliable. So for now, if we switch to this view, you could see that something is definitely not right there in terms of the surface kind of detail there, and the reason for that is because one thing that we capture in photometric normals, it also captures a lot of anisotropic effects there as well. And when you scan kind of props with complex shapes or natural shapes, different rendering engines would require different sets of normals for shadows, for geometry, then for diffuse lighting, for specular lighting, and by default we try to combine everything, so on average your prop would look about right in all engines. However, when you have a special case, when it's like we know it's super flat and we expect a certain look, that won't work out of the box. So we save our scene, and now let's go back to our settings, and under settings, if we scroll down, we would see this parameter and transfer radius, and what that does essentially, it takes low frequency data, basically higher scale data from a geometry, from a high poly mesh, and lower basically something with a larger radius, larger details from a high poly mesh, and smaller details from a photometric mesh, and it will try to do those corrections so the same normal map would work with all the processes. So in this case, we'll either can go ahead and set it to 0, or I'll just comment it out like so, save it, then we go back to our normal map, and let's delete our normal map and its tangent. We don't have to rebuild everything from scratch, we just rerun the build process, and it would grab uncorrected raw data and apply some minor adjustments to it. So now we just need to reopen our scene, and we could see right now, I keep in mind it's just a 1K, it's relatively low resolution, but we can see that right now as we move around that that our geometry stays like it looks like it's flat, and even if we just leave it like this and just move the light around, we see that it's that's what we see in real world. And of course the model here is a bit not quite accurate, but the material is, and this is just a 1K texture. So At this point, once we know that all the settings are good, it's usually good enough to go ahead and build the high resolution prop. I don't think that we'll build the whole 8K here. I think 4K just for this model. Let's close that. For this model would be enough for demonstration. So at this point, let's go ahead and click build for a 4K version. I'm going to keep it running and speed up the video for you, but you could see that a lot of things would be pre-cached, and in this case it will not do any downsampling of the source footage, use the original one, and you can see that the RAM utilization will go up. When building real props in real production, usually we use machines with at least 1 gig NVMe SSD drives, 128 gig of RAM. You can get away with 64, but it's gonna take forever. 96 is better, but you'll have hard time. 128 is good, and anything like up to 256 even better. You need a beefy video card. RTX 2070 2080 is probably the minimum to get reasonable inference times. We tend to use more latest at least 3080, 3070 and up. And on the CPU side, we need at least 16 cores, 32 threads. That's a good CPU, because a lot of image decoding, JPEG decoding happens on the CPU side while GPU is crunching the data. So in this case, we can see we only had a single loop, 12 images. That's also like the bare minimum to build any materials, even though the absolute minimum is just a single shot, and we'll get to that shortly. But in this case, you see it finishes up. We see the progress bar at the bottom there. It's finalizing, saving all the data. There you go, that is done. So let's fix up our albedo maps. As I said, it's not necessarily to do the it's not necessary to do this step, but as you will use it more, you can see that sometimes it's very beneficial to combine the two in the way we do it. That's done. We don't need displacement in this case. But let's build the AO. And what we see there in Blender, this AO is mostly used with an older kind of old school renders. Most of the current stuff uses more advanced techniques there. Obviously when you do path tracing and offline rendering, none of that is used. So this is mostly like for reference and things like Sketchfab, or when you put it on the fab. These things that are pre-baked are usually useful. Anyway, that's done. Let's open our model. In this case, it will import the scene and set up all the textures, and we would have everything set up here already. And you would see that now, yes, it's a much higher resolution maps here, and we have our roughness that we see it's pretty uniform, our reflectance, and we have example of this model on the Sketchfab as well. You can see a bunch of these artifacts, and that all that has to do with the fact that our original high poly mesh was so kind of noisy there. So typically when you get that height poly mesh, you want it to be as good as possible. In those cases you would need to do some smoothing and some filtering. That helps a lot there. Again, the confident map tells us that we could actually reuse that thing for materials, and in the next section we'll do just that. We will assume that we have just this 12 light positions, 24 shots, and build this material in much higher quality just from a single camera perspective. But once we also get to build in our octopus, like a properly scanned prop, you would see the geometry would be much better and the whole material definition would be much better than what you see here. But this is like the absolute minimum just to get to this point. And here you can see right now it uses material preview that uses real-time EV render, and we can also switch to cycles, and in this case it's path trace, and you would typically get the exact same results there. So at this point this will conclude this section of the tutorial of building the most basic prop, and in the next video we'll have a look at how to improve this further very quickly, just to get the highest resolution possible result for a 2D scan and then 2D process of the pipeline. I'll see you there.